Hello again. Here is another attempt of using the Spinal Gater algorithm for longitudinal data. So this time we're looking at another paper, an immune clock. Let's see, we find the title. An immune clock of human pregnancy. And here the data is somewhat bigger. It consists of 260 FCS files. And well, we'll try to do the same thing as we did in the first video, where I was looking at data from somewhere else, from cancer. So this time selecting the channels was done by me, just taking the things that usually are, that look like functional and lineage markers. And I fitted this with only 1,000 events per file, because we have 260 files, so this is 260,000 events. 260,000 events. We made a heat map and we did this interactive clustering. And then we are now about to save the clusters that we made, so we can make the next analysis of the sizes of clusters in individual FCS files. And I just want to go up here and point and say, well, it took 7 minutes just to load in the data. Load in 1,000 events from each file, because I had to load in everything. So this time we're going to spend the same amount of loading in the data again, and nothing saving. It's only 260,000 events. But then when you're going to do analysis of every individual file, this is going to take hours and not 20 minutes like before. So I will be back when I'm ready to do the longitudinal analysis of how the files and the clusters correspond. So, data is saved. I'm ready to go on. And so let's see, this is something old. We need to clear it like this. And then we load in, make a label expanding object. And now this thing is going to process how many? 260 files. So let us just stay for the minute it takes to do the first one, and then it will be 260 minutes more if we're lucky that it takes only 1 minute to do one. And so this will go overnight, and tomorrow morning I will show you how far it went, if it succeeded or if we have to do everything anew. Yeah, so what else do I want to say? So I have explained that I have some math up here that I take into account that FCS files don't all have the same size. So first I compensate for that, and then I say that I want not the colors to be kind of showing what happens across the clusters, only to show what happens across the files. So for each column consisting of files, I make the coloring as uniform or as nice as I can. Let's see. We didn't get to the next file yet. So probably we will very soon. I just saw that I don't have an image of myself here. I have it there. So let's keep it above everything else. And now I see that this thing seems to be doing something. So let's say this is running, and I'll be back when it's done. So it's morning, and the code is done. We have spent 5 hours and 40 minutes in order to make clusters of all these files. And I don't know how many cells we have, but we'll see in a short while. Because what I'm going to do now is I'm taking the labels for all the files and concatenate them. And I don't know, maybe I'm going to run out of memory because it's a lot of labels. And if that's the case, I'll do something clever. So let's ask for how many files do we have? Or not how many files, how many events. So we take all labels and ask how many are there of them. And now I have to count 3. Okay, 160 million cells. So let's see if we are able to make this matrix of this image showing from where do the cells come, or the clusters come, from which files do the clusters come. And I think it's actually going to work. Let's see. It takes a little time. That's maybe because it's a big image. Oh, I have a problem here. I have a problem. So I cannot see the names of the labels. I can see that there is something, there's some kind of pattern in this already, but I need to make the image a little bigger. So I think, how many times should it be bigger? 5 times bigger. And now it's not going to fit on the screen. That's a different issue. It wasn't big enough. I make it even bigger. Twice as big. So that's the problem with having a lot of files, and it's not going to fit on the screen. And maybe the file names are not the ones we want. So I think I want to sort it a little differently. I don't really care about the patients. I want to care about these stimuli. So let's see. I'll have to fix that. I'll just pause the video and fix that for a short while. So now I have ordered the names of the files in a way that seems to correspond a little bit to the clusters. So what did I do? I've took first the reagent that we used to as stimulus, and then there are some numbers. I put those in, and then there's I think it's the patient name or patient ID that comes last. And when I look at this image, it's too big for me to really see, but this is something we can fix. But I just look at the colors. I see there is a transition of colors here, so there is something going on with these 2 clusters. Let's go down and see if it transitions again. Yes, it transitions, and that's at another shift of names. Let's keep it. And it transitions again, exactly at a shift of name of stimuli. Was it here? I have forgotten now. Was it this one? Oh no, it was the next one. It was this one. But this one also transitions. Not as clearly, but we see that there's a lot of signal in these clusters. So here there's nothing, but we can just go to another one. So let's take this 51, 52. Is there anything to see? Oh yeah, it also shifts somewhere. So there's a lot of pattern here. And we can now go on and try to use our statistical tools or classification tools to see if Together, these clusters distinguish between the groups of samples, and just by looking at it with my naked eye, I believe this very strongly. So I don't really need much more proof than this to know that the sizes of the clusters and the treatments that the samples have been given are highly correlated. So I think this was a success. Let's see, there's nothing more I want to show you. And we need to learn how to make these images in a way that we can communicate, but that's always a little difficult. The thing we can do is we can put a number. So I will do this in another video on another day. I will use a classification tool to say how well do these clusters and their sizes discriminate between the different patient groups. So I'll pick out a random sample of the files, and I will see if I'm able to predict from the expressions which group these files come from.